Okay, so we're going to take a look at some examples dealing with regression. If you haven't printed out the blank template of these examples, do so now and put the video on pause. Alright, what I'd like you to do to start is enter the data set into Minitab. What we want to do is in column 1, C1, type in all the square footages. Title it X or square feet or whatever you want. I'm just going to title that X. Then type in all the prices into column C2. Now note here the prices, it says, are supposed to be in thousands. So the easiest thing to do is just correct that right off the bat. When it says 268 for the first price, enter that in as 268,000. Then we'll get the correct unit and not have to adjust later. Alright, so again, if you want to go through this, enter those into Minitab. Otherwise, listen to the video and then try to go back and do this on your own. Alright, so part A, does a linear relationship exist? Alright, what we want to avoid doing is just making a scatter plot and visually saying, yeah, it looks like either positive or negative linear correlation. Especially in the cases of small data sets, because in small data sets you need a relatively high correlation coefficient. You know, whether it's positive or negative. Negative just means negative linear correlation. So here's the process. In Minitab, we want to go to Stat, Basic Stats, Correlation, and have Minitab calculate the correlation coefficient. Alright, so when I do this, I'm getting R equals 0.929. That's a pretty high correlation coefficient. In general, what we want to do, though, is compare this to the critical value in Table 2. Alright, Table 2 is in the back of the textbook. It gives us the different critical values needed for the different sample sizes. So here in this data set, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different houses. So when I look up n equals 10, it's showing me that the critical value is 0.632. That means our correlation coefficient, if it's positive, has to be bigger than that. If our correlation coefficient is negative, just take the absolute value, basically ignore the negative sign. So even if this had been r equals negative 0.929, we'd say that still exceeds this value in the table. So we can say yes, a linear relationship exists. But if I ask you to do this on a quiz or test, you'd have to show all of that. Show what the R value is, look at Table 2, and then base your answer by the R comparison to Table 2. And now it says, if a linear relationship exists, find the equation of the regression line using Minitab. There's a couple different ways to do this in Minitab. I always have Minitab make what's called a fitted line plot. The way we get to that is we can pick stat and then pick regression. And then have it do the fitted line plot. Be careful, Minitab will ask you for the y variable first. A lot of people are always used to just putting x first. Select the y one, then select the x one, and then have it make the graph. The nice part is it shows you the scatter plot, the regression line. Above the graph it gives you the regression equation, and then off to the right it gives us a few values. The one that we need for our course is the middle one, the r squared. Here it just wants to find the equation of the regression line. So here's what I got. Y equals 98,203 plus 68.53 times x. Now, if you called the variables by name, if you wrote it in square feet and price or whatever, Minitab would display those in the regression equation. All right, so in part C, it wants us to interpret the slope of the regression line using the context specific to the problem. So let me just copy down again. That was my regression equation. The slope is always this number right here. Remember, in algebra you have y equals mx plus b, and m is the slope. What Minitab does is basically switches the order. Minitab gives you the y-intercept first, and then the slope attached to your x variable. So here the slope is positive 68.53. All right, so here's how we're going to interpret that. Remember, the slope is always supposed to be the change in y compared to the change in x from algebra. I can't just say it in an algebraic language manner, so I got to write it out in language specific to the problem. So the slope of 68.53 indicates that, well, positive means an increase. So there's an increase of 68.53 in the y variable. So what was the y variable? That was the cost of the house. So that's in dollars. All right, indicates that the price increases by $68.53 for each extra unit in x, and x was the square feet of the house. So for each extra square foot. All right, so interpreting the slope, we can kind of always use the same idea. Slope gives us a positive means it's an increase, negative a decrease in the y value for each extra unit in the x value. All right, so part D, it says, would it make sense to interpret the y-intercept? Well, let's think about what the y-intercept is. The y-intercept is where the graph crosses the y-axis. And a line would cross the y-axis when the x value is 0. So would it make sense to interpret the y-intercept? Ask yourself, can x possibly be 0? In this case, it can't. X is the number of square feet in the house. So a house can't have, not only can't it have 0, it can't have anything close even those tiny mini houses that are popular now typically have something like 300 square feet, not even close to 0. So no, it wouldn't make any sense to interpret the y-intercept. Right, next, they're asking us to predict the price of a home from this manufacturer that has a final layout of 1,850 square feet. Is this prediction reliable, and how do you know? Okay, if they want us to predict the price of a house, what we're going to do is just copy down the regression equation, except we're going to plug in a value for x. So I'm just copying down my regression equation, but instead of x, I'm going to put in the number 1,850. Now, one of the notations you'll see is that the book has this little caret on top of the y. And in statistics, that's actually read y hat. And that's used a lot when you're talking about a prediction or some kind of estimation. So you'll see that in the book quite a bit. Y hat equals, now I'm just going to punch this up on my calculator, 98,203 plus 68.53 times 1850. check this, make sure I didn't hit a number wrong, but we're going to put the dollar sign on there because we want to have the unit. I'm getting 224,983.50. All right, and again, just check me, make sure the calculator button pressing was right. You guys should definitely redo this on your own later. But that's my predicted Y value. That's my predicted price based on the relationship we see. Now it asks, is this prediction reliable and how do you know? All right, well, so far we found a high correlation coefficient. If you look at the graph, if you've actually made the graph already on Minitab, peek at it and notice that it looks like we have fairly strong positive linear correlation. If you haven't made the graph yet, just when you do, take a peek. You should get something that looks like it's strong linear correlation. So one way to answer this is the prediction is reliable since we have strong linear correlation. Now, when we get to part I will give us another way to answer this question. When we're asking about is a prediction reliable, there's typically two things we want to look at. We can either look at the strength of the linear correlation, and if it's strong, then our prediction's pretty reliable. If it's weak, our prediction's not reliable, but keep in mind, if you have really weak linear correlation, you wouldn't really use regression analysis anyway. Okay, so let's take a look at F. Would it be appropriate to use this regression equation to predict the cost of a home made by the manufacturer with 9,600 square feet? Well, what we got to do is see if that's actually a value that we observed, something close to it, in our sample data. So if we flip back to the data set, I'm not seeing anything even close to 9,600. The biggest square footage I see is 4,000. So this would not be a good idea since we only had homes that were 4,000 square feet or less in the sample. It's called extrapolation when you try to extend an observed relationship beyond the data. People do that a lot, but it's dangerous because you can't really assume that the linear relationship we observed on some chunk of values will extend to much different values. So no, we don't want to use that regression equation to make this prediction. Right, next it says in the sample there's a home with 2,700 square feet that costs $295,000. Is that price above or below average for a home its size and support your work? Okay. Well, let's figure out what we would consider average. To find the average price for a home with 2,700 square feet, plug 2,700 into your regression equation. The prediction that you get out of the regression equation is going to be considered the average Y value for that particular X value. All right, so again, we'll go to the calculator. I'm getting $283,234. So there's my average Y value. So we're above that, right? This is above average. So this price is above average for 2,700 square feet. 2,700 square feet. All right, then last but not least here, we got to talk about the coefficient of determination. Here it says, what is the value of the coefficient of determination, and what are two ways you could find it? The coefficient of determination is r squared. It's actually the square of the linear correlation coefficient. So one way to find the coefficient of determination is use the r value that we know. We had r equals 0.929. Keep in mind, Minitab rounds that off. So if I do it this way, and then square it by hand or square it on the calculator, I might get a tiny bit different result than when I show you the other way. Alright, so then r squared would be 0.929 squared. And again, we can punch this up on the calculator. It's like 0.863041. I'm getting something like this. Or if people like to write it as a percent, which some people do, Minitab does, then it's 86.3%. Alright, so that's one way to do it. The other way to do it is Minitab. On the fitted line plot, you can find something called r-SQ off on the right side of it. That's your r squared. So if I glance back at the fitted line plot, Minitab gives 86.2% on the fitted line plot. Again, they might be slightly off due to rounding, but not enough to worry about. Both of them would be perfectly fine. Now, what does the coefficient of determination tell us? Well, we can start by writing out basically the definition in the book. Coefficient of determination, whether you use 86.2 or 0.3, whatever, tells us that that percent of the variation in the y values But you know what? We shouldn't really say y values because it wants us to write this up in the context of the problem. So instead of y values, 86.2% of the variation in home prices is explained by the regression line, or by the linear relationship between the home price and square feet. Basically, that's saying if all the points, if you look at all the points on the regression line and look at the differences between those y values and the average y value, that those differences actually make up almost all, 86%, of the differences in the actual data points and the average y value. This is what the textbook gives as the definition. What r squared is oftentimes used for is answering that question before about is a prediction reliable. When the r squared value is high, that means that you have a good model. That would mean that your predictions are reliable because you have a good linear model. Alright, so a lot of different things that we can be asked to do regarding this linear regression. Let's take a look at another example. Alright, so again, if we look at the data set, hopefully you have it, the example problems printed out. We're looking at a sports scenario here. Right, a golf coach measured the swing speed, how fast in miles per hour the club head was moving when it hit the ball, and then the distance in yards the ball traveled for one of his better clients. First thing we're asked is, would it make more sense to have the speed or the distance as the explanatory variable? Well, the way I'm thinking about it is the faster you swing, it would seem like that would have an impact on the distance the ball traveled. So it makes more sense to me to make the speed the explanatory, which is our x, and the distance the response, which is y. Right, use Minitab to find the regression equation. So again, if we do this on Minitab, what we're going to have to do is in column 1, let's type in the speeds, call it x, call it speed, whatever you want. And then in column 2, let's type in the yards. Now, could have mentioned this in the last example too, but whenever you're doing regression, it's important you need to have the x and the y paired together. If you miss one of the data values when you type it in and you have the, like y column shifted one down, then the y values are no longer paired with the appropriate x value and you're going to get completely inaccurate results. So make sure you keep the list exactly as it appears. Okay, the equation I'm getting is either y equals, or if you like, the y hat that the book uses, either way. I'm just going to go with y because a lot of times I just do that anyway. All right, y equals negative 51.09 plus 2.920x. All right, so let me erase that. Get a better looking plus sign in there. Okay. Now let's see what we need to do for this one. Interpret the slope. All right, so it's another positive slope. Right, there's our slope again. A positive slope means an increase. So there's an increase in y, which was the distance in yards. So the distance tends to increase by 2.920 yards for each extra miles per hour in speed. All right, D. In the sample, there was a swing of 106 miles per hour that resulted in a 254-yard drive. Find the residual, and then what does this tell you about the distance? Okay, so the residual is your actual minus your predicted y value. All right, so our residual is going to require us to do some work first. We have to figure out what the predicted y value would be. All right, so we're going to take our regression equation, throw in the 106 as our x value, and again, go to the calculator to type this out. I'm getting my predicted y to equal 258.43 yards. And you always want to include the unit on your predicted. So here's my predicted. Our actual was 254. So my residual is 258.43 subtracted from the actual one, which was 254. That's looking to me like it's going to give us a negative value. Right? So we're going to end up with a negative value of 4.43. Negative 4.43 yards. What that tells me is that this drive was 4.43 yards below average for the speed. So really, that was asking us to do essentially the same thing we did in the previous problem about that one home value. Was it above or below average? This is really just a different way of asking the same question. I think we got one more part here. This is what you should have got for the fitted line plot in Minitab. It looks like we have pretty strong positive linear correlation once again, but it says notice that one point seems to be on a line with the others. That one right there looks like it's considerably farther away from the regression line than any of the others. So we're asked here, give a possible explanation for this observed value. Chances are I'm not going to, there aren't that many scenarios where I would do this to you on a test, because you sort of have to have some golf background to be able to think about this. Certainly how fast you swing does have something to do with how far the ball goes, but there are other factors. You have to hit the ball in the middle of the club face for it to give you the maximum distance. So if somebody swings really hard but has a very off-center hit, like barely catches the face of the club, it might not go very far. So that's going to be my guess at this. Maybe it was an off-center hit. Again, we can't possibly know for sure, but what we're trying to get at here essentially is we got this one data value that's farther away from the regression line than the others. That indicates that something may have been a little bit different going on there. So whatever, maybe a bug landed on him and distracted the person, whatever, but maybe he had an off-center hit and that kind of contributed to the short distance. All right, this chapter, regression and correlation, is always a little bit tricky for people, so take your time working through the homework problems and let me know if you get stuck. Good luck.